Hello everyone, today we are going to look at CAD lenses and how to simulate them in Fred. So CAD lenses, if you have a look, let's say at the RP Photonics Encyclopedia, you can find a good explanation. Basically, if you have a really intense optical pulse propagating through a nonlinear medium, if it is intense enough, then there will be some kind of nonlinearity in there. Then it creates a refractive index change in the medium, a nonlinear refractive index change, and this will depend on the intensity. So in the middle, where the pulse is more intense, it will be more refractive index change, and where it's less intense, there will be less change. Now, this kind of effect causes like a lensing effect, like gradient index lenses. They use basically the same thing. You have a material and it's basically flat, just the index changes over the diameter. Now, if you just have a normal Gaussian beam, it's easy to calculate the focal length of the lens, so it's easy to simulate it. But what happens really if you have different distribution? Yeah. So in my case, I have something like a ring beam, so something like this here, and this ring it's basically a collimated ring beam with a Gaussian distribution at the ring width, and I don't know what kind of effect this will cause in the optical design. So I was wondering how to simulate this, and I found a method. So to simulate this first, we have to do some calculations or plotting the actual beam profile, and we will have to do like coding or some scripting in Fred. So the beam, what it looks like. So basically, it's defined by its outer radius and the inner radius. So that one there and that one. And I calculate here basically the width and the mid radius. That's so far okay. The Gaussian distribution, sigma, what I will be using in the Gaussian plotting, will be slightly different, so not the full width half maximum. And of course, to calculate with the nonlinearity, you have to, it will depend on the intensity. Now, the intensity will depend on two things. So how much energy is in the pulse included, and how long is the pulse. So basically, the power intensity is like the peak power is the pulse energy divided by the pulse length. I've chosen for this example rather unrealistic values, just to see the effect better. So yeah, otherwise, if you would have like a much lower pulse energy and a longer pulse length, then you would have like a much longer focal length, and it would be really hard to see how it behaves in the simulation. Yes, so one more thing which you have to define is the material. That's this section here. So I've chosen here a material which is called M-Tier1 or IGP22, I think, from SHOT. This is a material with a really high refractive index at 1064 nanometers, and it also has a really high nonlinear refractive index. That will again help to visualize the effect better. So in Excel, what I did here, I basically just plotted the index, as a function of the radius, the radial distance from the middle. So there's the middle, and as you go outside, so as you go from the middle towards outside, you will see the raise of the refractive index because of this high intensity. So how this comes together, the index is basically the linear index plus the intensity um, in where is it? And the intensity in watts per square meters times the nonlinear refractive index, which is the other way around, square meters per watt. Yeah, this is so simple. Yeah. So one more thing, what you will need is the derivative by x and y. So the x direction is horizontal, and the y direction is the vertical direction. There won't be any difference really, because yeah, we are it's rotationally symmetric. But you will need the derivative, and if you give this Gaussian formula uh, to the Wolfram alpha, let's say, because that's where I calculated the derivative. Otherwise, I would probably make a mistake. And this is this ugly formula which came out of it. So if I derivate by x the formula of this Gaussian distribution, then I get this expression. That's of course the x, and if because x and y are symmetric, basically by derivating by y, you would get basically the x and y replaced in this expression. So 2cy and then the rest of it. Yeah. So now that we have the plot, yeah, and the for the refractive index and the derivative, then we can go to Fred. And in Fred there is I already opened it up here, and the materials. I added this material which is called KLM, which is a Kerr material. And basically what it does is you can select here a script gradient index material. So like I said, the behavior of this Kerr lens is very similar to the gradient index lenses. So you select that, and you will have to write some kind of script. I partially got this. I got this script earlier, like from CBS Europe, but I modified it with my own formula. So yeah, that's what it is. Basically, it includes a couple of parameters, input parameters, like the outer radius, the inner radius of this ring. Then then it will include the pulse energy and the pulse length in femtoseconds, and the pulse energy in microjoules, the linear index of the material, and the nonlinear index. So basically there are here 4 lines, which it just means you can select just by changing here the this constant to this variable here to 0, 1, 2, or 3. But now we selected 0, so basically this is the parameter set what we are working with. And to calculate the index, there is this function basically, which is calculating the index, and this function has multiple variables. So it has a x direction position, y direction position. If you want to give it a z direction position, then it has also that input. And then there is a couple more stuff here, which I think we are not really using. The wavelength, actually. Yeah, okay. The wavelength is basically included already in the plot by defining the linear and nonlinear refractive indexes. So it doesn't really matter. I included it here for some reason, but I could just delete it. Then you have the basically the plot, the refractive index expression. So this will be the refractive index depending on the x, y, and z positions. And there is here, okay, there's the imaginary part if you want to give an imaginary part for it, and there is the derivatives. So basically we will be using the derivatives in x and y. We will be using x and y as input, yeah, and we will be using the refractive index by position. And this little part here gives basically everything what I calculated in the Excel. So the midth of the ring, the width of the ring, the area of the ring to calculate the peak intensity. The peak intensity is here. So again, the very same formula what we had in the Excel. Yeah, and the Gaussian sigma, which is kind of often used here in the refractive index and the derivatives. So that's it, basically. So basically these are basically simple calculations based on the input pulse length and refractive index. And these here are the refractive index dependent on the x and y position. This is the x position, this is the y position, and this is the derivative or in x and y. Yeah. So this is how you define the material, and if you want to test the formulas, if they work properly, you can go on the test tab here, or test button. So if I go back to the Excel, let's say if I want to calculate the refractive index at 4, yeah, so 4 millimeters, I can just check this here. So x is 4, y, so it's basically to the right, and y is you can leave it 0. Perform test, and it gives me a refractive index of 2.747, which is, yeah, not exactly the same, but very close, yeah. So there is one more thing here which you have to be aware of, is the number of steps, yeah, and the resolution, because you will have like a cylindrical shaped material, and you will have like steps to which you want to resolve, yeah. So you want to have the material having different index at different distances from the middle, and this is the resolution. So the step size will be 0.01 millimeters, because millimeters are my system units, and the steps, I've chosen 1000 steps. I guess if you choose more steps, then the calculation will take just longer. Yeah, so I can send you this code part here if you want to, or the thread file. That's probably helpful, or the Excel file even. If you want to calculate ring beams, just drop me an email or a comment under the video, and I will send it to you. Yes, so the model itself is very simple. So I have a plane wave here, basically, and then I have a rod, which is at the moment 7 millimeters radius. So 7 millimeters, I just wanted to have it like, if I go back to the Excel, 7 millimeters is here, radius, so to cover the whole area. And the length of the rod is 1 millimeter. So you can take it longer if you yeah, you can take it longer. I used here 1 millimeter. Of course, the longer you take the longer the rod is, the shorter the focus gets. It's like has the kind of the same effect as changing the refractive index, yeah, up and down. And so that's so far the model. And there is, of course, here a few detector entities, if I make them traceable. So, and I also split the model in half, because it's going to be like a ring, so we would like to see something like a cross-sectional effect. Yeah, so there are basically a few detector entities here, and I figured out that there will be some kind of focus here. and I added here there like a horizontal detector entity. So for now I will just turn this off just to have a look at the beam. Unfortunately, this is a rather complicated formula, so the calculation takes some time. In this case, I'm just using 200 rays. Yeah, the 200 rays, if I calculate it now, with a single processor, of course, using the visualization, you can see that it took a few seconds. So when we are going up to 10,000 or more rays, it will take even more. So the interesting thing here, what we can see kind of immediately, is that there is some kind of focus here, like maybe even ring shaped close to the rod. And if I go further here, there's another focus there, and given distance, maybe let's make this active so that we can see a bit more. Yeah, calculating. Okay, so yeah, you can see that clearly there is a focus there. Clearly there is a focus there. So luckily I tested this earlier. Let's just delete this here for now. I tested this earlier, and I placed the detectors. That there is one here, and there is one there, and there is one kind of along this area. What happens when we change? What happens when we change the length of the rod? So with this rod length, I think we had a, how much was it? A millimeter? Yeah, 1 millimeter long long rod. We have here this focus at 56. Let's just do perspective view maybe. Yeah. So yeah, 57, 58. So yeah, somewhere around 60. There is a focus, and there is a focus here. Where is this focus? Okay, somewhere around here at the 22 millimeter position. That's a global coordinate. So 22 and 60. Just let's keep that in mind, and let's increase the length of this rod to double. If I do again tracing, 22 and 60, right? So I can immediately see that there is this focus, the further one moved to 36 millimeter global coordinate, and yeah, I'm not really sure about the other focus, but it seems to be very close, somewhere at 18, something like that, instead of 22. So both of the focus, the focal length moved a bit closer. Yeah, and of course the similar or the different effect. So if you the opposite effect happens if you reduce the length of the medium. So that's so far very good, because it's it matches the experience. Yeah. So the experimental things. So the one thing is remaining is to run the simulation with a bit more rays, and I can tell you that it will take a long time. But I will enable these here first. Make all traceable. Okay. And here we will use altogether 10,000 rays. Yeah, don't worry about the rest of here. It's like yeah, you probably know about it, but I've chosen to leave the inner 1 millimeter of the source hollow. Yeah, so it's basically similar to a ring beam anyway. What's going in? So if I click now OK, 10,000 rays, and I click quickly save, I will trace this through. It will take about 16 to 20 minutes. Yeah, and after it's done, we can continue and have a look what's happened here. Oh wow, that took some time. Okay, so now we have the results. This one for the 0.5 millimeter thickness, and this is for the 1 millimeter thickness. So, okay, now I will decrease the number of rays here again, so we can see something. It's a 200, that's good. And we will nicely turn these off, so let's keep rerunning it. It might not generate any more rubbish down there. Okay, so let's have a look. The first, okay, so this is what it is. If you there is a detector down there in horizontal direction, so maybe we can look at that first. And yeah, of course you can't get enough pixels, but interestingly, you have there a very, very short peak close to this, whatever it is, 11.7 position, and then it slowly yeah, kind of decreases, and yeah, it's almost zero at 50 millimeter distance, which is very surprising. I didn't expect that I have now. It kind of works as an hexagon, I would say. This is like a typical, this was like an incoherent simulation, but this is like a very typical, maybe like a bit more rounded curve would be typical for a yeah, for a basalt, yeah, from a hexagon. So very interesting indeed. If I go and have a look here close to it, so I have here a detector at 6 millimeters, so there. Then I can see that there is some kind of focus there, right? So the beam, so the 1 millimeter in the middle is like hollow, and the whole thing is like 7 millimeters, and yeah, of course that was the original beam, and I can see that there's some kind of focus developed here at 6 millimeters distance from the plate. So basically, you have a focus here, and you have a focus, kind of an hexagon type of focus further away. If we go further, so like let's say 10 millimeters, there was nothing there, but we can observe what's happening. So the ring got definitely larger. So I guess they're just expanding. We were in the beam waist there regarding the width of the beam. And if I keep going, so 15 millimeters, it's already quite a bit spread, but interestingly there is still a larger intensity around in the middle, you see. So at this part of the, so this is the second ring here, yeah, altogether, but there is still, the intensity is closer to the middle, is larger. I don't know how to explain that, or not at the moment at least. If we go further, not 20 millimeters distance, the ring is still like there is still getting stronger, I guess, and you can see that the ring, which is expanding, the width is like getting really large now. 33 millimeters. I wonder why I chose 33 just before the focus, I guess. Yeah, very interesting. So now at the moment, at the middle, there is basically no intensity, and we have now a second ring, a smaller diameter as previously. Not 47. I think 47 was the focus, yeah, where this huge peak was, and yeah, of course there is a peak with a small diameter in the middle. So even, what is it? Let's say a millimeter diameter spot in there. I'm not exactly sure that's like completely spot on the high peak, but yeah, there is apparently a focus, and of course there is this the rest of the beam around it as the ring is expanding. Okay, so I don't know what you expected, but I didn't expect all of these to happen. That's a very interesting little tool to simulate this. If you're building a laser, like or just want to simulate like a effects of a very intense laser pulse, this is a way to do it. Of course, this considers the fact that you know that at this position the beam, what it looks like. Yeah, if the beam is changing and or coming back to this area multiple times with different diameters, then you will have to change the model. So yeah, it is really not easy to simulate nonlinear index and nonlinear effects, but this is one way to do it. Okay, so I hope you enjoyed it, and don't forget to subscribe. Thank you for watching.